All right, class, now we're going to start chapter 10, which is all about inverse, exponential, and logarithmic functions. So the first thing I want us to talk about are inverse functions. So we need a little refresher. Remember that a relation is any set of ordered pairs, and a function is a relation for which each pairs have a distinct value of the first component for a distinct value of the second component, i.e. each x has only one y value, okay? That's the main thing. Each x has only one y value. If you've forgotten, the first couple times I talked about this, I brought up a vending machine. Vending machines are great. You push a button, like C6, you get out some chips. You push another button, D7, you get a soda. And you push E10 and you get candy, right? This vending machine works. I push a button, I get out a snack of some kind, okay? Now, this would still work, this vending machine would still work if instead I had both C6 and D7 going to chips, right? That would work. I push C6, I get chips. I push D7, I get chips. This vending machine would also work. Each x still has only one y. So these are our x's, these are our y's, right? When this vending machine wouldn't work is this. What if I had C6 going to both chips and soda? If I put C6, am I getting out chips? Am I getting out soda? I don't know, right? This is not a function because this one x value has two y values. So keep that in mind as we go on in this section. So the domain of a relation is all of the x values. The range of a relation is all of the y values. We already knew that. I say it all the time. Domain is our x values. Range is our y values. So let's go ahead and determine if these are functions. And I'm going to do that by making a little map of my x's going to my y's. So in this case, I have x's 1, 4, and negative 1. And I have y is 2, 5, and negative 2. 1 goes to 2, 4 goes to 5, negative 1 goes to negative 2. Is this a function? Yes, this is a function. Let's pick a more fun color. Okay, orange is fun. Now, I have another relation, right? We're going to call this relation G. It's a set of ordered pairs. I have x as negative 3, negative 2, negative 1, and 0. I have y as 5. Oh, I got another 5. I've already written that down. I don't need to write that down. 4 and 1. So I have negative 3 going to 5, negative 2 going to 5, negative 1 going to 4, and 0 going to 1. Is this a function? Okay, if I push a 3, I get a 5. If I push a negative 2, I get a 5. So even though I have two x's that have one y value, this vending machine would still work. So yes, this is a function. Last but certainly not least, let's look at relation H. I have x is negative 1, y is negative 2. Sorry, x is negative 1, negative 2, and negative 2. So I'm just going to write negative 2 once. Then I have y is 0, 2, and 1. I have negative 1 going to 0. I have negative 2 going to 2, and I have negative 2 going to 1. Will this vending machine work? No, it's not a function. Why is it not a function? Because negative 2, if I push negative 2, what am I getting out? Am I getting out a 2? Am I getting out a 1? I have no idea. So this is not a function. Remember, one way that we could show if something was function was the vertical line test, right? We would go through line by line and make sure that each x has only exactly one y, right? Like here's our x-axis, here's our y-axis. So this passes the vertical line test. So does this. This is a parabola. This, however, does not pass the vertical line test, right? Because instead of intersecting my graph at one point, it intersects at 2. A circle is also not a function. A function is one-to-one if each x value corresponds to only one y value. So here we have a function, not a function, right? This is not a function. This 2 goes to 2 values. This is not a function. Here we have a function. This vending machine still works. 2 goes to 8 and negative 2 goes to 8. If each x has exactly one y, then it's a one-to-one function. And one-to-one functions have inverses. Inverses, right? Inverses are something that undoes each other. Like the inverse of 3 is negative 3. So if I add them together, I get 0, right? This 3 and negative 3 are additive inverses. One undoes the other. So let's take a look at whether some functions are one-to-one. A good way to test if a function is one-to-one is if they are past the horizontal line test. So in order to be one-to-one, you have to be a function, right? You can't not be a function, so we can ignore all these guys over here. So let's do the horizontal line test. Here I have a line, something like y equals mx plus b. And if I go, if I go horizontally line by line, I see that my line only crosses at one point. So this is a one-to-one function. All lines, unless it's a horizontal line, are going to be a one-to-one function. Now, let's do our horizontal test for this. This is a parabola. This is something like y equals x plus c squared, right? This is a parabola. So I'm going to have to do my horizontal line test. But oh no, when y equals 2, it has 2 x values. So this is not a one-to-one function. So lines are one-to-one, parabolas are not. That means lines can have inverses. So let's figure out if these are one-to-one. So we already proved in an earlier slide that this was not a function, so I'm going to skip this one. I have x is 1, 4, and negative 1, and y is 2, 5, and negative 2. So x goes to 2, 4 goes to 5, and negative 1 goes to negative 2. So this is a one-to-one function. Here I have x is negative 3, negative 2, negative 1, and 0. Y is 5, 4, and 1. Well, because negative 3 and negative 2 both go to 5, this is a function, right? It's still a function. It's just not one-to-one, okay? So because this is a one-to-one function, it has something that will be its inverse, right? That will be its opposite. So the inverse of f, which we could write as f to the negative 1, that's how we're going to note inverses, just a little sneak peek. Instead of sending 1 to 2, it's going to send 2 to 1. Instead of sending 4 to 5, it's going to send 5 to 4. And instead of sending negative 1 to negative 2, it's going to send negative 2 to negative 1. This function undoes what this one did. So, in order to show that a function is one-to-one, we need to prove that if I substitute in two values into a function f of a and f of b, it's going to lead to the result a equals b. That's the way you prove functions are one-to-one. So if I have negative 4x plus 12, and I want to take f of a, let me erase that, I jumped the gun. So let's say I take f of a equals f of b. That means I'm substituting a into my function and b into my function. So I have negative 4a plus 12 equals negative 4b plus 12. And then I'm just trying to simplify like I normally would. I subtract 12 from both sides. I get negative 4a equals negative 4b. I go ahead and divide both sides by negative 4. I get a equals b. Boom. So this was a one-to-one function. Yes. And its graph is a line, right? So try and visualize these things. You could have already told me it's one-to-one because all lines are 1 to 1. All right, let's go ahead and try this. I need to show that f of A equals f of B. So I have f of x equals, f of A equals f of B. So I'm going to take f of the square root of 25 minus a squared equals the square root 25 minus b squared. Now how do I get rid of radicals? I square them because squares undo square roots. So I get 25 minus a squared equals 25 minus b squared. Okay, I have to subtract 25 from both sides. I get negative a squared equals negative b squared. I divide both sides by negative 1. I get a squared equals b squared. Okay, and I'm going to go ahead and take the square root of this. Now remember, with square roots, I can get both positive and negative square roots. So I get plus or minus a equals plus or minus b. And that's not really fair, right? Because I could have plugged in x equals 3 and x equals negative 3, and I would have gotten the same answer. So this is not a one-to-one function. So it doesn't have an inverse. Okay, so once I find out a function is one-to-one, I can find the inverse by doing the following. I change x and y, just like I had done in our ordered pairs. Remember, first 2 went to 1, but for the inverse, 1 goes to 2. So I go ahead and interchange x and y, and I solve for y, and I rewrite f of x as f to the negative 1 of x. This is going to be said, I'm going to say f inverse. So let's go ahead and try this. So f of x is 2x plus 5, so y equals 2x plus 5. We're just interchanging f of x for y. And now I need to solve, I need to interchange x and y. So this gives me x equals 2y plus 5. And solve for y. I subtract 5 from both sides. X minus 5 equals 2y. Divide both sides by 2. 1/2 x minus 5 halves equals y. This is my new function. So I can rewrite this as f inverse of x equals 1/2 x minus 5. Okay, first thing I need to do. For a one-to-one function defined by an equation y, find the inverse equation that goes with the following. So this is y equals x squared plus 2. This is why it's really important to visualize what's going on. This is a function, right? We know a parabola is a function. It's been vertically shifted up 2. But does this pass the horizontal line test? No. This is not one-to-one, so the inverse does not exist. All right, now what about a cubic? What do cubics look like? Well, remember, cubic functions kind of look like the walk like an Egyptian dance, right? Whoop. This passes the horizontal line test and the vertical line test. So we can go ahead and find the inverse. So the first thing I'm going to want to do is interchange x and y. So that gives me x equals y minus 2 cubed. Okay, I'm trying to get y minus 2 all by itself. So what undoes cubes? Cube roots. So now I have the cube root of x equals y minus 2. I add 2 to both sides. I find that the cube root of x plus 2 equals y. So f inverse of x is the cube root of x plus 2. Now, how can I tell if two functions are inverses? I can tell if two functions are inverses if when I perform the function composition of f in g, and g in f, I get x as my final answer. Okay, so let's go through an example. And this will also help us remember what function composition is. So if I want to take f composed with g, that's saying I want to take f of g of x. So what that is I take my function f, which is x cubed minus 1, and I plug in g of x for x. So I have the cube root of x plus 1 cubed minus 1. That gives me, cubes undo cube roots, that gives me x plus 1 minus 1, which is just x. Awesome. But I'm not done. I have to check this the other direction first. So I have to take g of f of x. That means I'm going to be plugging in f of x for x. So I have the cube root of x cubed minus 1 plus 1 equals the cube root of x cubed, which is x. So these functions are inverses. Now I wanted to go ahead and work through another example of how to determine if two functions are inverses in this second part of section 10.1. So I have that when I have two functions, if I do the function composition in both orders, I can find the inverse of, I can determine if they're inverses if when I take the function composition I get x. So here I'm going to take f composed g, and I'm going to take g composed f, and if they both equal x, then they're inverses. If I don't get x for the first one, I can stop because I already know they aren't inverses. So this is f of g of x. So I'm going to plug g of x into x. So I have negative 3 times negative 1/3 x minus 12 plus 12. That gives me, I distribute, that gives me a positive x plus 36 plus 12. That gives me x plus 48. Is that what I'm supposed to get? Are these inverses? Nope, not inverses. All right, let's try this again. Again, I'm going to take f composed with g, and I'm going to take g composed with f, and I want to find that both of these equal x. So I take f of g of x. So I'm plugging in g of x in for x over here. So that leaves me with 2x plus 4, but now I'm plugging in g of x. So I have 2 times 1/2 x minus 2. That gives me 2 times 1/2 x is just x. 2 times negative 2 is negative 4, plus 4 equals x. Awesome. Am I done? No, I got to do it the other direction. I have g of f of x, so that's 1/2 times x minus 2, so 1/2 2x plus 4 minus 2. That gives me 1/2 times 2x is x, 1/2 times 4 is 2, minus 2, I'm left with an x. So these functions are inverses. So some important facts about inverses. If a function is one-to-one, its inverse exists. It has to be out there, okay? Because what one does, the other undoes, if the range, the domain of f becomes the range of y. So the possible x values become the possible y values of the inverse, and the range of f becomes the domain of f inverse. That's because, remember I told you how it sends what was x and one y, it switches them, right? So this would be like the relation h, and this would be h inverse, it undoes h, okay? So because it flips points, if the point AB is on our function, then its opposite is on the inverse, Okay, and the graphs of these inverses are reflections of each other across the line y equals x. What does that mean? Okay, let me show you. So here we have the line y equals x. Like this is just the line y equals x with a slope of 1. So if I have a line that is f, if I reflect that across my y-axis, it's a pretty good reflection. That's f inverse.